Ashley, doing okay? Dylan? Gary doing okay? Well, that y prime bar is exactly the same as the y prime bar that we got up here. So this is really this signal. So now you can see why we're calling it a closed loop system. You can see here the loop. Okay? So if I have a P controller, this is a closed loop system. Why is what I have if it's a manual? If it's a manual, I'm setting U prime. So I'm setting U prime bar. If it's an automatic with P control, U prime changes in proportion to the error, and the error is the set point minus the measurement, which is the same that comes out. Clear, everyone? Sharon? Carlos? Carlos? Mika, okay? No? Sharon? Well, these are concepts. There's no example I can give you a concept. This is the concept. You can see that. Hopefully, I've understood this equation. I've been working the whole semester, right? We got this equation with the 4 steps, right? GUC transpose I minus AB to the minus DS, GDI is, right? So, this is always true. If my system is on manual, if the control is on manual, this is the entire story because I specify that U prime. But if it's an automatic, I'm not specifying the U prime, the controller is specifying. If I have proportional controller, U prime will be KCE. And what is E? Set point minus measurement.
Got it.
Good.
Oh, you wrote it down. Okay.
And that y prime bar is exactly the same as that. So you can see we have now a closed loop.
Should there be a prime there in that E?
No, E doesn't need a prime. E doesn't need a prime because the same E without just a difference, because they have the same nominal value, okay, is either y set point minus y or y prime set point minus y prime.
Oh, okay. Cool.
Mika, how are we doing? Good. All right. So that will be the picture if I have proportional. What if I have proportional integral control? For PI, remember I have U minus U naught equals KC E of t plus 1 over the integral time constant integral of the error. So let's Laplace transform this equation to get the controller transfer function. So using dictionary, what is U minus U naught? U prime. So obviously Laplace transform U prime is U prime bar equals Kc is a constant. Remember, constants factor out from Laplace transform. So Kc, and in the bracket, what do I have? Laplace transform of E is what? E bar. 1 over tau I is a constant. Now, integral. In the dictionary, you have that f equals integral, let's say, of g of r dr 0 to t. You get f bar g bar of s over s. So what's the integral of e of r dr? E bar over s, exactly. So the integral from the dictionary is E bar over S. Notice E bar now can factor out. So factoring out E bar, I have Kc 1 plus 1 over tau is times E bar, which can be rewritten as a function of S, a transfer function, with Gc of S equals Kc times 1 plus 1 over tau s. This is the controller transfer function for pi. With me? So how would that picture change if I have a pi control?
It wouldn't.
Well, something in the box would change. Instead of having Kc in that box, what would I have in that box? Kc times 1 plus 1 over tau is. Okay? Because now U prime bar is not Kc bar that was for proportional control. For proportional control we had Kc bar. Now we have Kc times the parenthesis E bar. Got it clear? So that picture would have, instead of just Kc, it would have Kc times 1 plus 1 over tau I. Yeah, just a second. So this is what I would have for pi. So the only thing that changes is what goes between U prime bar and E bar. That's what the controller does. That's what I'm designing. Finally, let's do ideal PID. Everything doing okay? Yeah. Good. So let's do now ideal PID. Let me write over here. Here I have the PID actually. Yeah, I'll do that. So ideal PID, we have that U of t minus U naught, which is U prime of t, is Kc E of t plus 1 over tau I integral from 0 to t of e plus now another term that has the derivative of dr. And that's called the derivative time constant. So integral time constant, derivative time constant. Another name used for integral time constant is reset time. So let's Laplace transform this. So left-hand side, U prime bar equals Kc is a constant, factors out. Kc. Then Laplace transform E is E bar. 1 over tau I factors out. We already saw that the Laplace transform of the integral is E bar over S. And tau t factors out. And what is the Laplace of the derivative? Then a lot of times, s times the Laplace of the function minus the function at time 0. So that would be s times e bar, which is the derivative e, minus e of 0. What am I going to do with that e of 0?
That integral, that r, what does that r stand for? Like,
Because it's a definite integral, you can use any,
can Kc depend
any
on r?
symbol you want. You want to use y, use y. You want to use dummy variable. Definite integrals have dummy variables inside. Right?
Is Kc always a number?
Yes.
Okay.
Case is always a number, tau I is always a number, tau d is always a number.
Okay.
So the e is 0, just be 0.
You could have been
Exactly.
E of t,
We're assuming
but
initial.
for some reason, E of
Implied
changes
assumption.
the
If
variable.
we're talking about
Yeah,
transfer
one.
function, there's always the implied assumption. Any deviation, and the error is again, y prime will be 0, y prime separated will be 0.
Why
Right?
why do you write it that way? If it's a what do you mean by dummy variable? What is that? It's just I don't understand. You're confusing me.
By what?
The dummy variable, that integral is confusing.
You need to review calculus. I don't know what else to tell you.
Well, why can't you just I don't know. All right, never mind. I'll ask you after class.
Review calculus, take your calculus book and review definite integrals.
I,
Okay, here, integral 0 to 5 of x dx is equal integral 0 to 5 of y dy is integral 0 to 5 of w dw. Any symbol you want to use here is the same thing.
yeah, right. But what is that
You
function?
should avoid though something that is here. If this is t, the only thing you should be using here is t.
But what does that function stands for? What is that function ever going to be something?
No, it's just the integral of that. So I can use here any symbol I want except t.
I'll ask you after class.
That's the only thing that is not allowed in the definite integral. If you have variables on the limits, inside you shouldn't be using the symbol of those variables. It will be something totally different. I don't know what else I can tell you on this. You understand that? Doesn't matter what symbol you use in the definite integral.
Oh yeah, no, I understand that. I'll ask
And
you
you
after class.
must not use, because I have t here, I shouldn't use t.
No, I'll ask you after class. Don't worry.
All right, let's continue. All right. So, as Adam said, implied assumption kills this one. And now I can factor e bar out. Now I have equals Kc 1 plus 1 over tau is plus tau d times s, all that times e bar, which can be rewritten as gc of s times e bar, where gc of s is kc 1 plus 1 over tau is plus tau ds. Felix, okay?
Mm-hmm.
Good. Bring. Bring. So, in that picture, if I have the idea, this would change. For any controller, what goes in here is the transfer function. For any controller, what is here is the gc of s, which is just kc for p, kc times 1 plus 1 over tau is for pi, and add plus tau ds if you have ideal PA. Okay? Josh, question?
So it just changes to Kc times K in parentheses.
Yes, exactly. So this is the transfer function function for ideal PID. Okay, this is TF for ideal PID. Okay. All right. Time for a big constant.
Ah, dang.
On purpose, I used 2 different colors here. Everything. Inputs is what from the environment affects my process. If I have the controller on manual, I'm part of the environment. I'm setting U prime bar, and U prime is an input. However, if I'm under automatic control, I'm no longer setting U prime. What is affecting this picture here from the environment? Look at this picture. Tell me what is being affected from the environment. The disturbance is certainly coming from the environment. What else is coming from outside?
Disturbance?
Set point. Exactly. The boundaries of the closed loop system.
What? What was that? Did you hide those crayons pretty well?
Hmm?
Never mind. Keep
I'm hiding my.
I saw, yeah, no. You hide them pretty well.
Well, it disappeared. When I had it here, it disappeared.
That was so funny.
I didn't even notice.
What is he doing? Is he farting or something?
This is closed loop boundaries. Open loop boundaries is white boundary is open loop boundaries. Now, for linear systems, we always have a transfer function representation. If the system is open loop, meaning that I'm setting U prime bar, equation 1 tells the whole story. But when I have feedback, the inputs, instead of being disturbance, are still inputs. But U prime bar, U prime is no longer an input. It's replaced by the set point. That's what comes from out. And the feedback control, what comes from outside that affects the process, is the set point. So for closed loop, I will have closed loop transfer functions. And we'll get them in a minute. Let me make it crystal clear, hopefully. Open loop, which means controller in mind. We have Y prime bar equals GU of S, U prime bar, plus GD1 of S, D1 prime bar, plus GDR of S, dr prime bar. We have a transfer function for each input to the system, manipulated or otherwise. That's the equation 1 that I have up there. That's all stuff. 1, yes.
Should that Y prime bar be in the circle? The purple circle, the one on the right? Because you said they're
No,
the same.
it's output. It's coming out.
So those two Y's are different.
No, they're the same. They're exactly the same thing. But it's still an output still coming out. So it's going in here, but it's coming out. This part is returning it, but it's also coming out.
Okay.
All right. Now, closed loop. Please definitely have this in your notes, guys. Okay? Closed loop means controlling automatic.